Well, welcome back. We're in Vectors and Projectile Unit Worksheet number 1, question number 3. Can you get two vectors of unequal magnitude ever add up to give the zero vector, or give a vector that has a magnitude or length of 0? Can three unequal vectors, under what conditions? Okay, so let's go ahead and let's look into that. That's interesting. So let's start with the same one that we've been doing thus far. Let's say v1 is 10 and going to the right. Can I get another one to add up to be 0? Well, we know from the first example that if I put it exactly opposite of that, that'll add up to be 0, but we can't because it says unequal magnitude. So we can go through each one of these things. Well, what if I made this shorter here? Well, that won't be 0. And what if I made this longer? Well, clearly that won't be 0. So, and if I did it at an angle here, just like we did in the previous one here, if I made v2 to be -5, go ahead and see question number 2, and you'll want to prove that that doesn't add up to be 0 either. Even if that became -10, that still doesn't come to be 0, it becomes to be something else. So it sure seems like if we have two vectors, the sum total can't be 0, so no to that first question there. But now this brings up an interesting one. Can three unequal vectors? And by unequal, let's go ahead and let's assume that each one is unequal from one another. So they're all unique lengths there. Let's see if we can do that one. Let's start with the same base. v1 is 10, because why not? And if I add something of unequal length there, so let's say that the v2 is -6, and if I throw in another one here, it looks like I'm going to be able to do it. v3 will be -4, and then boom, boom, boom. That gives me a total velocity, in this case, of 0, or a resultant vector of 0. So it looks like we can do it. Yay! In the case of 3, that's a bad smiley face. He's all crooked. That's much better. Under what conditions? Well, we got in a one-dimensional case here, so we have a 1D case here. We can do that where the two going the opposite direction add up to be just the same magnitude, but now have the opposite direction of the original vector, so that will work. I could clearly mirror this and flip that around and that'll all work, or have it go up and down instead, and it'll all still be one-dimensional. Now, the curious question, even just for myself, is can you do that in 2 dimensions? Well, if you do it in 1, it seems probable that you'd be able to do it in 2 dimensions, but sometimes the geometry becomes a little bit crazy. So let's try it out. I don't know. Let's do v1 is equal to 10 again and see if I can get some other 2 going on there. Now, if I make it like this, maybe I can do it like that. I don't know. Let's try it out. What if v2 was equal? Now, see, I don't think that's going to work all of a sudden. I'm just trying to think it through here. I don't think that's going to work, because then I could put, well, I'd have to do it the other way. If I put this one, oh no, that will work. Oh yeah, cool. What if I made v3 go that way? Now check this out. This is how I drew v3 is incorrect, is quote unquote incorrect, or bells should be going off in your head, or if you talk to yourself like 2 months from now when you've done a bunch of these, bells then would go off in your head about v3. Why is that? Let's take a little break to the side here. Normally, this is what you would see. Normally, you would have some. Let me do it in the same orientation. Normally, you'd have some. Let's say this is a velocity of something going down, and we'll say that it has like a speed of 20 meters per second. Why not? And if I said, hey, it's going at some angle there. You'd go, oh, I bet it'd be helpful to be able to get the component vectors of this and figure out how much is going in the x direction and how much is going in the y direction, you might say. Or if you remember from class there, instead of labeling a new variable vx and vy, I could instead just replace that with the things I already know. I already know that it's going to be the hypotenuse times the cosine of alpha in this case, and this one over here is going to be 20 sine of alpha. Okay, great. Now I could go and find those. Now check this out. This diagram right here is distinctly different than this one over here. Can you spot the difference? And let me get a different color so we can spot the difference. And the difference is, notice that for the normal resultant vector, it starts at the tail of one and ends at the tip of the other. The total vector, you might say, is starting from where the first one starts and then ends where the other one ends. It's pointing, you could say, hey, these velocities are going to the right and they're going down, and this black one has a velocity that's going, I don't know, like down and to the right at some angle, right? And they all of those directions there match up with one another. But if you look back over here in what I just drew, this is distinctly different. Because let's look at it from the legs of the triangle, right? This velocity is going to the right in the green, and then the blue one's going down. And so then like the resultant vector for just the green and the blue added together would go the opposite direction of V3 there, because V3 would have to go to like down and to the right. However, you can read this the way V3 is already listed there, and that's the velocity going like up and to the left. Well, those are opposite in direction from these guys right here. So really be careful if you ever see something like this. Throughout this course, it's most likely wrong. Now, in this case, we're trying to actually add 3 different vectors together. And so these are my 3 vectors that I added together. And I did it this way because these are actually going to cancel out one another. If we look at V3, and can I take red, and then I'll make it like lighter. Oh no, I'd have to like get this right up here. Okay, cool. Now I can look at the component vectors of V3 here. And if I look at that, I'm just going to label it as V3 x direction and V3 y direction. And if we look at that, we go, hey, look at the length of V3x and the length of V1. Well, they look like the same length, right? Especially if I was like perfect at drawing this. And furthermore, they're the opposite directions of one another. That means that V1 is going to be equal and opposite of V3x. And look at the y versions there as well. Sure looks like V2 is going to be equal and opposite of V3y, and it will be. That means that when I add these two together, right, instead of thinking about the original or the original V3 vector, I could instead replace this with just its components, and it would be the exact same thing. So now if this is the same length as that, and this one's the same length as this one, notice I'm borrowing a geometry trick there. Of the 2 ticks means that the other thing with 2 ticks is the same length, and the length is the magnitude in this case. That when we add these 2 vertical bits up, they're going to cancel out to be 0. So you could even say that like Vy total is going to be 0, and Vx total then, when I flip those around from how I wrote it before, Vy total would be 0, and Vx total would be 0. Well, now when I go ahead and add these 2 components of whatever my resultant is going to be, clearly it's going to be equal to 0. Do Pythagorean theorem of 0 squared plus 0 squared, square root of that, and you just get 0. So can we add that up in 2 dimensions and get 0? The answer is yes. Can we do it in 3? I highly, highly suspect the answer is yes on that one as well. But I'm not going to go into that because that's pretty hard to draw anyways, and we won't be doing the 3 dimensions in this class, so don't worry about that. That's it. Have a beautiful day. See ya.